Hi guys. Something interesting. Cooks are scientists. I would rather say they are better scientists. Now, why are they better scientists? Let me prove my statement. Now, a cook requires what all? Requires ingredients like vegetables, uh, potato, tomato, all those ingredients required. Along with that, also requires spices and then some water or maybe milk sometimes. It's being cooked in oil, and a vessel obviously in which they cook it. Now if it takes hell of a long time for cooking, then maybe they will use pressure cooker. And if they are not using pressure cooker, and if the food takes pretty long time to cook, I would add some ingredients to it which would quicken the product formation, like soda or something of that sort. Now let's talk about a scientist. A scientist also does the same thing. A scientist also has ingredients, main ingredients. Along with that, they also add reagents. Now reagents, along with reagents, also solvents are required. Solvents could be water also, could be ethanol, propanol, diisopropyl ether, or butanol, or chloroform solvent. And the reaction, if it takes hell of a long time, then maybe can use autoclave. Autoclave is just very much closer to pressure cooker. Reaction done in pressure is autoclave. Obviously, we also would be using catalyst to quicken the reaction. Right? Now, why do I call a cook superior to a scientist? Why? Because see, a scientist would weigh everything to absolute accuracy, millimole level or milligram level, and add to get the product. What does a cook do? Approximation to perfection. Alright, so they don't have any pan or they don't weigh it, they directly add it, but still you get the taste. So their product are out of approximation to perfection. Whereas in our case, in case of scientists, we are weighing to accuracy and then creating the product. Now, further, a scientist's job is what? Exploration, obviously. Explore what? New process, or if it is old process, that process is modified further for improvement, or new product. Same is also done by cook. So cook does all those things which a scientist does. Scientist does everything at measurable level, whereas cook does it with approximation to perfection. Right? So who's better? Alright, anyway, now let's proceed ahead. In this video, I am going to present my work on propranolol, synthesis of chiral propranolol, chemoenzymatic process. Alright, so would explain chemoenzymatic process, kinetic resolution, and then ways how I would be dealing it with molecular modeling. Now, one thing I would like to clarify over here, that I am not explaining the mechanism. I am just explaining how using model you can explain a particular reaction, alright, in steps. Right, so it's purely molecular modeling, alright, and I hope you would enjoy it. And then maybe sometimes again I would also explain mechanism. That would be in some other video, but here it is purely colorful balls and sticks used for modeling. I hope you enjoy it. Let's see how it goes. Okay, before we get into it, you already saw pictures of some ball and stick model structures which I am going to use Now, prior to getting into it, you have got to know that there are some color codes that has been used. Now, green color is for chlorine, black is for carbon, red is for oxygen, and blue is for nitrogen. We also have hydrogen. In case of hydrogen, it would be like white ball with a bond, all right, as presented in the pic beside. Let's understand structure of epichlorohydrin. In case of epichlorohydrin, we have got CH2Cl, we have got CH2 and Cl, and then we have something interesting over here. This is called as epoxide linkage. COC, the cyclic structure. This is epoxide, so it has got epoxide COC bond, all right, and then one H over here CH and two H's over here, that is two H's over here, that is CH2s. Now this is what is epichlorohydrin. And why epichlorohydrin? Epichlorohydrin because chloro and epoxide, so it's called as epichlorohydrin. Let's understand model of alpha naphthol. Now in case of alpha naphthol, what we find is two fused aromatic rings. Then every carbon, this black ball, it represents carbon, white represents hydrogen, and red one represents oxygen. So we find that this carbon in the alpha position has hydroxy attached. In the alpha position, it has got hydroxy attached. All right, and then we have got hydrogen all around the carbon. All right, so all around all the carbon which are there, they have got hydrogen bond. All right, and then we also see consecutive double bonds. All right, that's what we will be observing over here. So consecutive double bonds. So this is the three-dimensional structure, modular structure of alpha naphthol. Let's understand structure of acetyl chloride. In case of acetyl chloride, we have C double bond O Cl linkage, C double bond O, C double bond O Cl linkage, and then we also have that carbonyl chloride linked to methyl group, that is C with 3 H's. So that carbonyl chloride group linked to another carbon which is a methyl group, CHHH, carbon attached to 3 hydrogens. Alright, carbon attached to 3 hydrogens. Let's understand the structure of N-butanol. Now it has got CH3s there. So it has got CH3s over here. Then it has got CH2s over here. It has got CH2s over there. Another CH2 over there. Another CH2 over there. Then it has got CH2 and OH. Alright. So CH2 and OH. That makes it normal butanol. 1, 2, 3, 4 carbon and an alcohol, butanol, in a straight chain. So it is normal butanol. This is the structure of diisopropyl ether. Oxygen, oxygen, carbon, 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 carbon. 2 carbon are attached. Methyl groups, 2 methyl groups. 2 methyl groups are attached to this carbon. And to this carbon is attached H. Similarly, this side also carbon attached H, CH3s, 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 CH3s. Alright, so this is the molecule that we are going to use it as solvent. Alright, so this is what is diisopropyl ether. Let's try and recap what we had done regarding enantiomers, optical isomers. first and foremost requirement is the carbon which is there has to have 4 different groups attached to it. So we find it here, 4 different groups. This carbon also has 4 different groups. Apart from that, this molecule is mirror image of this. Alright. So approved for chirality and approved also for enantiomer. Alright. Why? Because a molecule, in order to be chiral, has to have 4 different groups attached. 4 different groups attached, which we have, and it has to be non-superimposable. Now this both being mirror image of each other, owing to which they are not superimposable. Okay. Now how do we assign S and how do we assign R? It's all based as per Kahn-Ingold-Prelog system. It's all based on atomic weight ranking. Now we know iodine, which is there, is the largest, all right, atomic weight wise, and when we come to bromine, it is medium, and chlorine is smallest. All right, so LMS goes this way. If we draw an arrow, LMS, it goes this way. This is counterclockwise. Now whenever it goes counterclockwise, it's S isomer. Whereas in this case, what we observe is your LMS is going this way. LMS is going this way. This is clockwise, and hence it's R isomer. Alright, so this is just a recap which we had done earlier in my earlier videos. Now this is what I'm going to apply to propranolol. I presume you would understand it well. Now this is the concept, which same concept we are going to apply to propranolol. Let's understand the structure of propranolol. Alright. Here let's understand the chirality of propranolol. Alright. Now prior to that, let's just review structure a bit. This is naphtaloxy. That's what we find over here, naphtaloxy. Alright, this is naphtaloxy. Then we have got propane. So 1, 2, 3, propanol. We have got propanol group attached over here to this oxygen. To this oxygen, we have got propanol group attached to this oxygen, propanol group attached. Fine. And then here we have got nitrogen NH, to which isopropyl group is attached. Alright, so isopropylamine, propanol, and naphthaloxy group. Alright, these are separate, right? Appears to be attached. It's not. Alright, now we are interested in chirality. Now, as we are interested in chirality, which is the chiral carbon? When we check out over here, this carbon has got this group different. It has got this group different, and it has got OH here, and it has got H here. So this carbon is chiral carbon. So that's what we are talking about, this carbon. Alright, so this is what we talked about, naphthaloxy group. Then we talked about here we have got OH. Alright, this carbon is attached to OH, attached to H behind, and then it is attached, this carbon is attached to isopropyl amine part. So what do we find? We find that this carbon, or rather this carbon, has got 4 different groups attached to it, so that makes it chiral. Fine, that's okay. But which isomer, R or S? Now let's check out over here, and then we go in there. Now since this both are carbon, so bit of confusion. So what do? We check out the adjacent atom. Now adjacent atom over here is nitrogen, adjacent atom over here is oxygen. So nitrogen and oxygen. We know nitrogen, when we talk about nitrogen in comparison to oxygen is smaller. So we assume this to be smallest group. We assume this to be medium group, and obviously this to be the largest group. So that So if I show it in model over here, so this O, the largest, then this C, medium, this C, smallest. So now if we draw an arrow, now it would be this way. Now this arrow is all based on atomic weight ranking. Alright, so when we do as per atomic weight ranking, when we draw an arrow, we find that goes counterclockwise. Whenever this happens as per Kahn-Ingold-Prelog system, we assign it to be S isomer. Alright. So here when we find, it would be in this direction. Similarly, when we go to model, we would find that this would go in this direction. Alright. Now this direction. Alright. So this is what is S isomer. Interestingly, if I just topple this, what would happen is that OH would come down. Alright. So if it comes down, then that becomes R isomer. Alright. So whenever we are synthesizing propranolol in absence of chiral catalyst, we end up with mixture of R and S. Alright. Here what we have done is we have synthesized propranolol using enzyme as catalyst. Now enzyme is one of the best chiral catalyst. Alright, using this we have been able to synthesize both the optical isomers of propranolol. Alright, let's see whether I can just topple it and show you. Now see, I've tried my level best. Now I've just toppled it, right? So O has come down. So O, as per our atomic weight ranking, O was the largest. And this is nitrogen, right? And this was the smallest. Alright. This group was the smallest group. This was the largest group. And this was the medium group. So this carbon, we assign it to be medium. And this carbon is the smallest. There's no change in this. Only O has shifted from top to bottom. Now when this happens is, this is L, so this is L, this is M, and this is S. So what we find is, now the arrow goes clockwise direction. So when arrow goes clockwise direction, that is what is R isomer. Alright, so that is what is R isomer. Alright, so that's what I was saying, that whenever we synthesize molecules having chirality without chiral catalyst, we always end up with R and S. Another interesting thing that we observe is this is the molecule. Alright, now I am going to replace this isopropyl amine group by Cl group. Right? Now let's see. Now this isopropyl amine group is removed, and to this is attached Cl group. So Cl is attached to this. Alright. Now when Cl is attached to this, now what happens is, now see this carbon, Cl being atomic weight wise higher than oxygen, so now this carbon gets the status of medium. This carbon which was there earlier was the smallest owing to nitrogen being attached, but now since Cl is being attached, so this becomes medium and this carbon becomes the smallest. Alright, now we are talking about this carbon becomes the smallest, which was earlier medium. Alright, so if I draw LMS now as per Kahn-Ingold-Prelog system, atomic weight ranking wise, then what I would observe is it would be large, medium, small. Alright, so it would be in right direction, or it would be clockwise. Now if it is clockwise, then that becomes R isomer. So this just by changing group. Why? Because when we change group, the adjacent from Cl changed to amine, right? Cl changed to amine, so owing to which it lost its position of being the smallest, and now it gained the position of being medium, this carbon. All right, I hope this helps you understanding Kahn-Ingold Prelog system. Nevertheless, I'm going to use this also in my reactions when I'm going to present in my next video. You just got introduced to varieties of chemicals, its molecular model, which I'm going to use for synthesis of propranolol. Now, as I explained, I'm not going to explain any mechanism. Maybe I'll use it some other times. But here I am going to use all model for explaining synthesis of propranolol. The process that I am going to explain is chemoenzymatic process. Chemo, because these are all chemicals that I am going to use, and enzyme is going to be my catalyst. So I call it as chemoenzymatic process. Now enzymes are chiral, so it's very enantioselective selective. Now in this process we got both the isomers of very high optical purity. We got R also very high optical purity, S isomer also very high optical purity. Now and the biggest significance is that R isomer is being used as contraceptive and S isomer is beta blocker. So both the isomers have significant pharmaceutical role in our biological system. Alright, that's one part. Now the next part is that since I'm going to deal with chiral propranolol, so it's very much essential for you to know about chirality. Alright, yes, if you are all already aware about it, please I beg your pardon, but I thought that why not just recapitulate the basic part of chirality, which I did, and then I will also put it on propranolol and try to express to you how the structure molecular model of R propranolol would be and S propranolol would be. This work of mine got accepted in Journal of Organic Chemistry and American Chemical Society publication. Now this publication of mine received lots of viewership, good citations, and one I would like to express is it also received place in Kirk Othmer's Encyclopedia of Chemical Technology. Now I have got lots of such scientific work which I am going to represent in form of videos. I hope you would enjoy. So the forthcoming video, as I told, I was planning to have it in one, but since this became pretty long, so I thought why not divide it into two parts. So the next part is synthesis. Alright, hope you enjoy that also.